So the acetic acid one is a times 10 to the negative fifth, and we're looking for cyanic, and this one is 10 to the negative 10th. So hydrocyanic is 5 orders of magnitude weaker than acetic acid. So let's go back over here. Nope, there we go. So it's this one, and this is a 10 to the negative fifth, and this is a 10 to the negative 10th. So much stronger. It's not a strong acid. It's still a weak acid, but it's much stronger than the hydrocyanic. What would be the pH after adding 15 milliliters to 2 molar to blah, blah, blah. Okay, so I need, for pH, I need the concentration in moles per liter of hydronium ion. So let's see, I need 2 moles per liter. And then we had 0.015 liters. So the liters cancel out, and we get 0.03 moles of OH minus. So if I divide this by half a liter, 15 plus 485. I get 0.1. So this is 0.1 molar. So that's going to, of hydroxide. And so if I take the negative log of the OH, which is 0.1, or the other way to write this would be, make it even easier, would be 1 times 10 to the negative 1. You'd end up with a pOH of 1. So then my pH will be equal to 13. Is everybody okay with that? Or any questions about that?
Why did you do the 1 times 10? Why didn't you just do the 0.1?
It was really easy to see when I do 1 times 10 to the minus 1, because I know that the 1 doesn't matter because, you know, it's multiplication and it's a 1. And then the 10 gets canceled out with the log, and then the negative signs turn into a positive.
Okay.
No other reason.
So we can basically see the answer.
You can
with
see
the 1 times 10.
yeah, you can see the answer before you even do it. Exactly. Okay, so let's see. We've got what would be the pH after adding this one? Okay, so same kind of question. 6 moles per liter of hydrochloric acid, and we've got 0.025, no, 0.0025 liters. So 6 times 0.0025. And then we're going to divide that by 1.5025 liters. Is that right? 2.5 milliliters added to that? Yep. So we're going to get divided by 1.5025. So 0.00998 molar, in this case H plus. So just take the negative log of that. I get 2. So my pH is 2. So both of those pHs changed dramatically. And so now we're going to check to see how it would change with this last problem, except instead of it being pure water, it's going to be a buffered solution with hydrogen carbonate and carbonic acid. So initially, let's check what the pH is going to be before we do anything. So it's, I think it's 6.35. Just a sec, let me let Jeff in.
Good old Jeff. Such a nice guy.
6.35 plus, and this would be the log of the base. Or in this case, the salt. So it would be 2.9, and then this would be 0.65. And it works out to be, pretty sure it works out to be 7. 6.35 plus log 2.9 divided by 0.65. Close parentheses equals, yeah. All right, so I got a pH of 7 here.
Mr. Gay,
Yeah.
why is it not a negative log?
Because the equation is plus log.
Oh, okay.
It's pH is equal to pKa plus log of salt divided by acid. Negative log, that's the Henderson-Hasselbalch equation. The negative log is just what we use for pH.
Okay, cool.
Okay, so we know we're going to start at 7. Like the last problem, we started at 7 and moved to 2. So we're going to see if we get such a dramatic change again. And since it's in a buffer, probably not. So we need to know the moles of everything. So we already know the moles of hydrochloric acid. It's 0.015. So we need to know the moles of carbonic acid and hydrogen carbonate. So we'll do 0.65 moles of H2CO3 per liter, and it's in 1.5 liters. And so we get 0.975 moles of H plus. Sorry, not H plus, of carbonic acid. And then we have 2.9 moles per liter of baking soda. And it's also in 1.5 liters. So 2.9 times 1.5. So we have 4.35 moles of hydrogen carbonate. All right, so then we need to do an ice table. So initial change, equilibrium, H2CO3 here, and HCO3 negative here. So this is number of moles is 0.975, and this number of moles is 4.35. What is this thing that we're added going to be interacting with? This hydrochloric acid here, this 0.015 molar hydrochloric acid, is it going to react with the carbonic acid or the hydrogen carbonate?
The hydrogen carbonate.
Can somebody tell me why? He's right. Because it's an acid. So this H plus is not going to react with an acid. Acids don't react with each other. And this guy here is negatively charged. So this positive charge and this negative charge come together to form carbonic acid. So we end up gaining 0.015 carbonic acid, and we end up losing 0.015 hydrogen carbonate. So this is 4.245, I think. And so then we're going to use this Henderson-Hasselbalch equation again with our new numbers. So we have pH is equal to 6.35 plus log of 4.245 divided by 0.98. All right, so 6.35 plus log of 4.2545 divided by 0.98 close parentheses. And the pH is, how many sig figs we have? 2.
2.
6.98
7.
665. So I've got I don't know. It actually
Wouldn't it be 7?
it actually just rounds to a pH of 7. It looks like we only have 1 sig fig because of the 6 molar.
Oh.
So I mean, you can see significant figure wise, it's so insignificant that it actually doesn't count for the change in pH. So this is a good buffer. pH didn't really change, which is what the buffer is supposed to be doing, opposing a change in pH. All right, so we're looking for lysine. What do these all have in common? Or what is lysine?
Lysine is a I totally forgot the name. The natural molecules that are in the body.
Amino acid.
Amino acid.
Yeah.
It's from Jurassic Park.
It's amino acid from Jurassic Park. That's why I pick it, because
Lysine contingency.
people remember the lysine contingency. This is a thing. I mean, it's kind of silly that they call it the lysine contingency, because you have a built-in lysine contingency in several other amino acids.
Yeah.
If you don't get lysine, you also die. So if there's no lysine available, then you're going to have some bad diseases. So you end up with an N with a couple of electrons here, a hydrogen, and a carbon, and a hydrogen, and a carbon doubly bonded to an oxygen, bonded to an oxygen, bonded to a hydrogen. And this is the generic amino acid structure. And then what's attached is the R group, which dictates what functionality that amino acid is going to have. The R group is here. Why is the R group in this position? Because that carbon has 4 bonds, that nitrogen already has 3 bonds, that oxygen already has 2 bonds, and this carbon here only had 3 bonds, so it needs a 4th bond. So I've got a hydrogen, carbon, hydrogen, hydrogen, carbon, hydrogen. Do this a few times. And then a nitrogen with hydrogens and a lone pair. Okay, so when this goes into water, the pH is going to rise. Can somebody explain to me why?
Because that last nitrogen has those negatively charged electrons, so that it would attract the positive hydrogen ions.
Okay, so it can actually grab a hydrogen off a water molecule, and this can become positively charged. And then what's left behind is a hydroxide. So more hydroxide means pH goes up. You okay with that?
Yep.
Anybody want to comment on anything else with this?
The sides, the N on the left side and the H on the right side.
Yeah, what's going on here? What about that lone pair of electrons? We talked about this lone pair down here, but what about this lone pair up here?
So because of that H that can detach on the right side, or not, yeah, it would technically detach and then just go to the other side. And
so then it kind of neutralized itself, right?
Mm-hmm.
Okay, so the base structure for the amino acid doesn't really change the pH. It's the side, the R group, that dictates if it's going to be acidic or basic. And lysine is one of the basic amino acids. Also one of the essential amino acids.
I still don't get why they never enacted that in the movie.
Because they were all dead.
But life finds a way. And Jeff Goldblum shirtless, best part of that movie.
Rob, what were you saying about the R group? What does it do? It decides
what the functionality is. So all of the amino acids all the amino acids have this part here, everything that I'm circling. And then all the amino acids have some other thing here. And this other thing here is what dictates what that amino acid is going to be. So there's
Okay.
20 amino acids, and we've got 20 different R groups. It can be as simple as just a hydrogen, and that would be glycine, or it could be complicated like a lysine or like a glutamic acid or something like that, where there's a lot more to the side chain, or a proline, or a
Okay.
tyrosinase.
Thank you.
Let me grab. Let's see. Q. Can we? Why is this not letting me zoom in? I hate this newer version. Can I just not see it? Full screen it? No, that's not helpful. All right, so how about if I'll just do this. Open with.
I mean, I can zoom in on it on my screen.
Yeah,
I'm sure others could too.
I'm not sure why it's not letting me. All right, can we see that?
Mm-hmm.
So there's a black portion of the molecule and a blue portion of the molecule, and you can see that the black portion of the molecule is the same for each of the different amino acids. And then the thing that's the side chain is like this CH3 group, which makes this alanine. So if I'm a amino acid and my R group is CH3, I'm automatically alanine. If it's a branch chain down here where there's a C with an H on it and then two CH3s coming off, then that's valine. Or valine. And then glycine is a super simple one here that's just got an H on. Tryptophan is much more complicated. It's got a couple of ring structures. Serone's got an alcohol group. Cysteine has a thiol group on it, which is an SH, which is the thing that's really hard to get out of plants. That's usually the thing that vegetarians or vegans, that's how they have nutritional deficiencies, are the sulfur-bearing amino acids, which is methionine and cysteine. Okay, that's all I got with that. Kill you. Come over here. Okay, so we ended last time doing those buffer problems. Do we have questions about the buffer problems? Are you guys feeling comfortable with those?
So I don't understand why we made an ice box. I don't understand what the purpose of that was.
We need to know how. I'll just go back to that. We need to know how the two substances concentrations are going to change. So I know that I'm adding. This hydrochloric acid, the 6 molar hydrochloric acid. So I've got this acid that I need to get rid of because I'm a buffer solution and I'm trying to maintain my pH. And when the acid goes in, the pH should go up. And it doesn't go up because I have this buffer system. And my buffer system is composed of this hydrogen carbonate and this carbonic acid. So it's going to interact with one of those two pieces of my buffer, and we already said that it's going to interact with the hydrogen carbonate. But it does reduce the amount of hydrogen carbonate. So I started with this much hydrogen carbonate here, 4.35. I ended with 4.245. So I used the ice table to determine this new concentration here, or this new amount of moles of hydrogen carbonate. So then I can plug these two numbers into my Henderson-Hasselbalch equation and get my new pH.
Okay, so why did we do the Hasselbalch equation in the first place the first time.
We wanted to know what the pH was going to be before we added the hydrochloric acid.
Okay.
So
Thank
we asked what happened to the pH, right? So you wouldn't be able to tell me what happened to the pH if you didn't know what the pH was before we did anything to it. Does that make sense?
Yeah, that makes sense. Thank you.
Sure. Something else with those buffer problems? Everybody, okay, let's see. Could we do another one? Still a little confusing me. Yeah, absolutely, no problem. Let's find one. Let's go, I don't know, worksheets, acid base, buffers. I don't see a good one in this worksheet. I'll find another one. But while I'm looking, I want you guys to read this question and be able to answer it for me.
Shouldn't you add the acid? Because that's like one of our safe chemistry rules.
This person is trying to like kill somebody. So
I know, but like, what if the acid? Okay.
if a buffer solution.
How many milliliters of base is there?
That's what it's asking you. That's
How
that's
much is it?
that's the question.
Hmm.
Nobody wants to answer this question?
Oh, we're answering. My guess is C.
C. Anybody else?
1000.
I was thinking.
That's what you were thinking, or you're still thinking?
Well, that's what I kind of came up with.
All right, let me copy this. Click over here, go here, go on new page. Control V. Okay, so what's the difference between pH 5 and pH 10?
5 orders of magnitude.
Okay, so if I've got a 7, go to 6, go to 5, 8, 9, 10. So how much more concentrated is 5 than 7?
2.
100,000.
100 times more concentrated, right? Because this is 10 to the negative 7th, and this is 10 to the negative 5th. How about 10? What's the difference between 7 and 10?
1,000.
1,000. Okay, so 10 is 1,000 times more concentrated than 7, and 5 is 100 times more concentrated than 7 in the other direction. So moving from 7 to 10 is 10 times more change than moving from 7 to 5. Did that make sense?
5.
You, you were right the first time,
See?
Kalina. Okay, let's look at it like this. I got 7, right? And somebody gives me something with a pH of 6. And then I also have another container that's got pH 8 in it. This container here is 10 milliliters. How much 8 do I need to cancel out this 6?
2,
You okay with that?
10.
10 milliliters, because this makes me 10 times more acidic. And if I put the exact same amount of base in, that's 10 times more acidic, then they both cancel each other out. We okay with
Okay.
that? So what if I go 2 steps this direction?
Then it would be 100 times more acidic.
And then what if I go 3 steps this direction?
1,000 times more acidic.
So over here, it's 1,000 times more acidic. Over here, it's 100 times more acidic. So what's the difference here?
2,
10,
10.
right? If I take 100 and I multiply it by 10, I get 1,000. So that means that this 10 here is 10 times more basic than 6 is acidic. Sorry, 5. Sorry, we're talking about 5. Then 5 is acidic. So if
the
I've
answer
got
is A.
if I've got 100 milliliters of this stuff, I only need milliliters. I only need 10 milliliters of this stuff. Why? Because this is 10 times more concentrated.
The acid, the pH of 5 is 10 times more concentrated.
No, no. The base is 10 times more concentrated because I moved 3 pH units away from 7 on my base, and I only moved 2 pH units away on my acid. It's so hard for me to get a feel for the
So-
room.
You get from 5 to 6 to 7 to 8 to 9 to 10. 10 is our base, 5 is our acid. So what I don't understand is why whenever you go from 10 to 9, that's not because in your example you're like skipping numbers.
I'm not skipping any numbers. No numbers were skipped.
You went from 5 to 7. You skipped over 6. In the very top one, the one above the problem.
Why is it 100 times? Because to go from 6 to 7, it's 10 times more concentrated. To go from,
Oh, okay.
that's 10 times. So 10 times, 10 times, 10 times.
10 times.
So each time I move a unit away from the middle, I'm 10 times more concentrated in that direction. So a pH of 10 is 1,000 times removed from pH 7, and a pH 5 is only 100 times removed. No?
No, I'm just working it out in my brain. I mean, I can see what you mean.
So are we good?
Yeah.
Anybody want to ask a question about that?
That makes sense.
I wish I wasn't the only person asking questions.
Speaking of that, there's a discussion that's going around with instructors about this being a replacement for an online for a face-to-face class, and the thinking is that some instructors might require a video link for the students. Thoughts?
What do you mean, like everyone has to use their webcam?
Yes.
I have a class like that.
Lee
I mean, yeah,
Hancock's?
my psych class does that, but also like I feel like you shouldn't really. I feel like you should just encourage it. You shouldn't really force it, because then you might.
But you
get
were going
more
to be
people
there in
sitting-
person anyway, and everybody was going to see you anyway.
Yeah, but I just feel like it's different, and then there's more people that are willing to just skip the class because of it. Because I know some people who just absolutely hate being on camera. I don't really mind it because I do it for my psych class all the time. I would prefer that everyone had their webcam open and everyone participated, but I don't feel like it should be like super enforced. But I feel like it would be nice if it wasn't just me and
How about you
Mr.
people who
Van
don't have
and-
webcams?
Please spare me.
I'm using my
Whatever,
phone.
you're great.
Guys, every one of us has a phone, so you don't really have an excuse.
I don't have a webcam.
Because I don't even have internet.
Yeah, you
so
don't.
I
You don't
can't-
need a webcam. You can just use your phone. I mean,
Yeah,
Yeah.
you can get the Zoom app and use it just like that.
I'm assuming you can use your phone.
The quality probably isn't as great, but
It's
Yours
better.
is pretty good.
It's
I mean,
better.
You're pretty good.
You're probably spending like $10 on your webcam, maybe $20 on your webcam, and the camera on your phone is going to be much higher resolution than your webcam. Like this webcam is just 1080, and my phone is at least 2.5K.
It takes off like 20 years.
What? Oh,
Because
this
you
web.
can't see your
The
face,
worst-
so it takes off
the
20
worst-
years.
The
Gotcha.
worse your web camera is, the younger you look. Because I feel like y'all can see my acne and stuff.
It's like an old movie where the main female person comes on and they glow the screen.
I don't know if I'm speaking just for myself here, but I 10 out of 10 look like Smeagol every day I'm home by myself, and it only gets
Hey,
But you
Betty,
were
my hair.
you were not going to
Betty,
look
my
like
hair
like
currently is
if
not brushed.
if this
Look at mine.
virus thing
It's
didn't
awful.
happen, you would have gone to class. So
Yeah, but I would have like
go ahead.
I would
So
have
if
I don't know, not looked like a bespectacled egg in class. So
Yeah,
like,
but you could have done that anyway.
yeah,
You
'Cause,
could
like,
still
I
do
don't-
that, and
my
you
hair-
still save time because you didn't have to drive.
I love
I'm
that
like
part.
in a hoodie, dude, and my hair isn't brushed, and like my face is gross. But like,
I'm not wearing any pants.
no one wants
needs
to
to know
that. Sorry, but no.
All right, so before
Dave is the most comfortable.
before Ethan jumps on us, let's move on to a problem.
Feel the wrath.
Control A, Control C, new, Control V. All right,
He's complaining to
so
me right now.
go.
Okay.
He's not allowed to complain because he doesn't have his webcam on. That's my decree. All right, you have I don't know, 4 minutes. All right, so let's see.
Fair enough.
So 4.10 plus
0.7.
Hop on it, babe. You won't get sunburned. All right, you guys done?
Almost.
Yeah, almost.
No. Is this one of those problems with the ice thing?
Yeah.
Okay, cool.
Are you not reading the chat?
There's a chat?
Yeah.
Or not that, but there have been chats.
This lady that lives in Mount Hood bakes a whole bunch of loaves of different kinds of sourdough bread and sells them to people in the area every week. It's amazing.
So you just always have good sourdough bread?
Yes, yes, we do. For the past couple of maybe 6 weeks. So the answer is 0.03. You guys got that?
Rob, you're making me want to break quarantine for bread. It's rude.
I'm sorry. Just bake some.
Does she sell sourdough starter?
She probably does, but no reason to ask when she's just making it. We are getting a sourdough starter for somebody else, but it's supposedly for tortillas.
Sourdough tortillas?
They're so good.
I've never had it, but that's what I hear. That's all I've heard is they're so good.
Wouldn't they be like puffy?
Puffy?
Like,
Fatima, does
Like-
that mean yes, you're all over sourdough tortillas? All right, that's what I just did.
uh, um,
So I
so
took
how did you get the 4.10?
the 4 point what?
The pH.
It's from that pH table.
That's not pH. That 410 is the pKa.
pKa.
Thank you.
The pKa
So-
comes off of this
That table.
table
The,
right here.
yeah, the big.
So there it is right there. It's like a pen in not that color. 410.
Why did you use the 4.10 instead of the 4.76?
Because that's
Because
acetic
that's
acid?
acetic acid.
Oh, sorry, I was reading the wrong acid then. Whoops.
Because I like vitamin C and not vinegar.
I like vinegar.
Ew.
So where'd that thing go? Here, there, there, there. Where'd I put that?
Close some of your tabs.
There it is. So are you okay with the 4.40 for the pH before anything happened? Anybody have any questions about 4.40 as our starting point?
Why would we?
Why would you have any questions? I don't know.
I
I don't have
don't know.
any.
You just sometimes you like ask us if we have a question because
Oh
there's an
yeah,
important
you're right.
thing
Yeah.
that we're not seeing.
Okay. That's fair.
Are the bases always supposed to go on the top?
Yep.
Okay.
The salt
Then
will,
that's what I did wrong.
the salt will always go on the top.
I just picked the wrong acid. Otherwise, I did it fine.
Good job, Ethan.
Real quick, Rob, if you're starting from the PKB for whatever reason, would they be flipped then?
You would
For the POH?
You would no, you needed to be in PK. Huh. Yeah, that would work if you or if you flop the sign. If you just subtracted the log, then that'd be the same thing. Are you guys okay with these numbers here? The 1.125? Like this is the salt concentration times the volume, and then the acid concentration times the volume, and then the what do we have? Potassium hydroxide concentration times its volume, getting all those numbers, filling in our ice table, subtracting. I subtracted it from the acid because potassium hydroxide is a base, so we would lose acid, and then we'd end up with this much left over, and then we'd increase the amount of salt because we reacted some of the acid, and then I plugged those numbers in down here, and so my change was 0.03.
How did you get the KOH concentration?
On the question, it said I've got 1.5 molar potassium hydroxide, and I had 18 milliliters of that.
I guess I just didn't see that. What does the HA and the A with a negative symbol? I know it's like the something about the acid, but
HA is the generic form for any weak acid, or any acid for that matter. The H is the acid portion of it, and then the A is the anion that the acid attaches itself to. So if the H has come off, what I'm left with is an anion. So probably a polyatomic ion, but it's a negatively charged particle.
okay.
Any questions on that?
No. I think I'm starting
Allison
to
did
get
in
it.
the ice table.
Sure. The ICE stands for initial, change, and equilibrium. So initially, we had this buffer sitting there, and we needed to know what the number of moles of acid and of base, in this case salt, were before anything happened. So I calculated out the amount of the salt that's in the solution, and I came up with 1.125, and I calculated out the amount of moles of acid I had in the solution, ascorbic acid, which is 0.5625. So that was my starting position. And so initially I was there, and then I'm going to change that buffer by adding this potassium hydroxide. And when I did that, the potassium hydroxide reacted with the acid, the ascorbic acid, and it turned that ascorbic acid into the anion, ascorbate. So then I lose some acid and I gain some anion, And that's when it's reformed its equilibrium after I've reacted out all of the potassium hydroxide. So we added this potassium hydroxide to the solution. And what we've seen before when we add a strong base to like pure water, the pH goes really high. Well, it didn't because it was reacted with and not it didn't end up changing the pH but 0.03 because I have the buffer system in place. So it just stands for initial change in equilibrium. I'm sitting there waiting for something to happen. Something happens, and now after the thing has happened, what do I have left? What's the aftermath of that? Is that good, Allison? The problems are all super similar.
Another
So-
practice problem.
So I'll do this. I'm going to change this number here to, I don't know, 950. I'm going to change this to 5. I'll change this to 1.25 molar, and then, I don't know, butanoic. A very, very stinky weak acid. And then I'll do sodium butanate. And we'll say, I don't know, we'll have a 4.5 molar of that stuff. And we're going to add, I don't know, say 25 milliliters of 0.75 hydrobromic acid. So I have this buffer. It's going to be buffering at a particular pH. Then I'm going to add an acid to it. So the pH is going to go down. But because it's a buffered solution, the pH is going to go down very little. So it's 327. I'm going to be back in 5 minutes. Feel free to talk amongst yourselves. I won't be in the room. I'll just leave a dog.
So we take the pH of butanoic acid.
What was that?
We take the pH of butanoic acid, right? Or the pKa.
Yeah, it's on the table.
Yep.
Wait, would it be like 0.975 liters, or would it be 0.95 liters since we added the 25 milliliters? Or would it be 0.95? I'm trying to figure out the liters for.
Since we're working with the concentrations, don't you just use the original amount to figure out the number of moles of the substance?
Yeah.
That's what I'm
Yes.
thinking. Okay.
Done?
Almost. I'm on the ice
Almost.
portion.
Yeah, I'm almost finished with the iceberg.
What is that about? Don't.
Iceman's coming for you. Give it to you.
All right, so let's see. It's 4.5 divided by 1.25 log. What was the pKa?
4.83.
4.83. All right, so I got 4.83 plus log. Don't do that. Skip. 4.5 divided by 1.25. So the initial was 5.39, and I got 4.5 mole per liter times 0.95 liters, and 1.25 mole per liter times 0.95 liters, and 0.75 moles per liter times 0.025 liters. 0.75 times 0.025. 0.01875. 1.25 times 0.95. 1.1875. 4.5 times 0.95. 4.275. So ice, this is going to be plus 0.01875 minus 0.01875. And you are 4.275. You're 1.1875. And that's HA, and that's A negative. So minus that, I get 4.256, and I get clear that minus that. We got 1.169, so 4.83 plus log of that number divided by that number. Close parentheses equals. Okay, so I got 5.391.
I got 5.85. Damn it. You said 5.39?
Yep. So this is
To what point, Allison? Just how? I have like a step-by-step process where you start at the pH and then you figure out all the moles and stuff. Don't bang your head on the table, which is step 2. And then step 3 is ice, and then step 4 is the pH number. So if you break it down into steps, it's a bit easier. But I got the wrong answer, so, or maybe the wrong answer, so. I don't know if I'm correct. So what did you get for the concentration of what number did you get for the concentration of the acid?
1.1875.
Okay, and for the salt?
4.275.
Cool. And for the
0.01875.
0.01875? Oh, I know what I did wrong.
That's what I got.
Okay. So 0.7. It was 0.75 moles per liter.
Oh, okay.
So wait, for HBr, it was 0.7 moles per liter, right?
I don't know. 0.75 moles per liter.
Times 0.95.
No. You didn't add 950 milliliters of it. You only added 25 milliliters of it.
Yeah, I got on a rut. Okay, so it would be 0.975, right?
No, you only added 25 milliliters. So look at your screen. 0.025. This right here.
Oh, 0.025. So it would be 0.975. Oh, we're not doing the combination. We're just doing the amount of. Okay, cool.
Yeah.
So I have a question.
Sure.
You said that the base is on top, correct?
Yep.
If we're adding an acid, why is the base's molar number going up?
It didn't go up. It went down.
It went from 4.5 to 4.756 in that.
No, it went from 4. No. Come on. You know I have horrible penmanship. Look over here.
2, not a 7.
This is a 2. 4.256. That's a 2. If it was a 7, it would have this stupid line through it. So I can differentiate myself between 2s and 7s of my own handwriting.
I do the same
Okay.
thing.
I do the same thing.
Can't think of my Z's.
Huh. Me, Gage, and Jeff. Is this just like a problem tall people have?
With what? Your handwriting?
Yeah. Are those two things inversely proportional to each other? The taller you get, the worse your
No.
handwriting is?
Oh no, I got
No,
top of my
well,
third
at
grade
least-
teacher.
At least not in women, because whenever I meet any girl, even if she's short or super tall, she always has like typically really good handwriting.
I think
Maybe it's
maybe
just
the
in men.
curve is just
Oh.
a little different. Maybe it's the opposite for women. Who knows?
I realized what I was doing wrong. I accidentally changed 4.256 to 4.365. I have dyslexia.
Okay, I'm almost done.
How did I get 1.169? Where's 1.169? Oh, I added it.
And you said 5.39, right?
That doesn't seem right. Wait a second. Allison's pointing something out. Or, wait, no, McKenna's pointing something out. And I might have. Oh, yeah, because I hit the subtraction key twice. That's a problem. All right, so that's supposed to be added. So then it's supposed to be 4.83 plus log of that one divided by that one, close parentheses. It's 5.38.
95?
5.38.
Okay, so you have pH is equal to 4.83 plus log of 4.29375.
Yeah, hey, just a second. Just a second.
Okay.
I wonder if I can draw on this thing right here. Can I draw on this? Oh God, what is that? Don't do that. Stop. All right, this is what I'm gonna do. I gotta downloads.
Oh, your sig figs are just closer to the decimal than mine.
Open Paint because it's amazing. Bring this over here. All right, so I made a mistake here. I didn't add. Make that red. I didn't actually add it. All right, make that much thicker. So this number is wrong. This number is supposed to be 1.206. And I should have recognized it because I was adding and this number went down instead of up. So then I took that number and I plugged that number in there, and then this number becomes 5.38. So the pH did indeed go down by a very small amount. So nice work, McKenna. She keeps catching me on stuff, by the way, which is good.
I have a question. Why did you add on the acid side and subtract on the
What did
acid?
because I added an acid. And so all right, so what do we use? Butanoic acid? All right, so just can expand this thing out so I can draw.
Instead of adding a base to what?
All right, so all of the buffers have a weak acid and a salt of the weak acid, okay?
Yes.
In this case, our addition was hydrobromic acid, which means we're really just adding H+, okay?
Okay.
What is this thing here going to react with? This or this?
What is what thing going to react?
This.
I wasn't watching.
The H+. What's the H+ going to react with? The HA or the A-?
The A-.
Sure, because one's negative and one's positive. And when these two things react and come together, what do they make?
Sorry, I keep like writing as you're talking, and so like okay, there we go. What?
Does that make sense?
Oh yeah. Minus.
So it's always going to be the same with these buffer problems. Whatever the change is, one of the two is going to go up and one of the two is going to go down by the same amount.
Okay, so whenever you add an acid or an H+ technically, then you're adding on the
acid side.
Acid side.
Because I added an acid.
But when you add a base, you add on the anion side because you're adding a base.
Because I'm adding a base. And I'm losing acid because the acid is now reacting with the base.
Okay. So I'm feeling all
Also,
good.
I have a quick question. Why do you not turn, because those numbers are mole numbers.
That's a really good question, and I'm good with that. We've got, so it was, dang it, why is that not working? So pH equals 4.83 plus log, and then I'm going to write this really big so we can see what's going on here. So the Henderson-Hasselbalch equation says moles per liter, and I'm only putting in the moles and not the moles per liter. So let's watch what happens here. So the moles for this one, for the salt, was 4.256 moles, and the moles for the acid was actually 1.206 moles. All right. If I wanted moles per liter, then I'd have to divide by the volume, and in this case, the volume would be, what was it? 950 and 25. Is that right? So 0.975 liters. But so would the denominator.
So they just cancel?
Yeah, just like mathematically, this is a fraction on top of a fraction, and this is a fraction on the bottom of the fraction, and both the denominators are the exact same value. So they literally just cancel out. Feel free to include it, but it's not going to change your work. I don't put it in there because it simply mathematically cancels out, and it causes you to have to do 2 more steps.
Okay, thank you. That's why I was confused on that. Thank you.
Yeah. No,
No.
I'm not going to do another one. But
Jeez,
you are going to do
Allison.
another one for your homework. So then we're going to do another one on Tuesday when we do homework review.
Allison.
Jeez.
Let's do.
Don't falter for wanting to understand.
I know, but we did too. Just do another one, change the numbers. He's recording this, just watch it over and over again.
Rob, don't you have a sheet with a bunch of these equations in the Moodle?
Yeah.
Usually, yeah,
I do.
usually you do.
So here you go, Allison.
Oh.
I've watched the Khan Academy video of this one before, and it's good. He does a good job. He's got a lot of good people working for him. Okay. So we haven't actually talked about anything new today. Yeah.
No.
And that's totally
We
fine
have-
because if I'm not mistaken, we have like tons of time.
We've got like 40 minutes, maybe 30.
No, I just mean like for before the first exam.
Are we doing 2 sets of notes before the
Yes.
exam or just this one?
2 sets of notes. We're gonna do aqueous as well.
Cool.
All right, so blood pH, super important, obviously, because you don't want to die, and that's usually what kills people. So the individual reactions associated with the buffering system for blood pH are carbon dioxide gas turns into carbon dioxide aqueous, and then carbon dioxide aqueous reacts with water liquid to make carbonic acid, and then carbonic acid plus water produces hydrogen carbonate and hydronium ion. So that leaves us with this overall reaction. We're not going to do any calculations with this. It's just for your edification. The interesting part about this is, so let's say that somehow you were exposed and you breathed in a bunch of acid. So you walked into a room and somebody had, I don't know, hydrochloric acid in a gas. You were one of those guys who was trying to isolate elements, and you created a bunch of a toxic something or other in the air. So in this case, if you added a bunch of H plus to this, what's going to happen? This guy right here is going to react with that. And now that just disappeared out of the solution. So what ends up happening is the equilibrium here is skewed. It's supposed to be an equilibrium. Now there's too much of this. So from last quarter, what's this equilibrium reaction going to do?
Oh, it's gonna try and
I'm totally
push that out.
I'm totally sorry. This goes down. This went down because it reacted with. So what's going to happen?
It'll try and replace that. and
This
go-
reaction is going to shift in this direction, right? We okay with that? To replace
because
this?
Yeah.
So now that means that this thing went down and this thing went down. So what happens to this equilibrium?
It shifts.
It shifts in that direction. So the carbon dioxide gas that you would normally breathe out, you wouldn't. You would keep it in your system. So if you get exposed to an acid or a base and you breathed it in, what should you do?
Breathe out.
You should breathe. You should go someplace of fresh air and breathe. And that's the first thing that a firefighter will tell you. If you've been in a fire or exposed to a chemical, get out of the space, go to a space with fresh air and just breathe. And if the person's unconscious, they will take them out on a stretcher and drag them someplace where there's fresh air and they'll bag them. So they're breathing for them. The most important thing is to make sure that you have the correct gases transferring back and forth inside of your own system. So your body takes care of it yourself. So if you've been exposed to something acid or base wise and as a gas, if you just walk away from it and start breathing, everything will be fine. So the moral of the story is don't stop breathing, and you should be fine.
Don't stop. Breathe. That reminds me of your diving story where you like keep breathing out because you breathed in so much.
Yeah, the scuba thing. Yep.
Scuba thing.
Okay, so here are a couple of reactions that are acid base that you could find happening out and about. The first one is so we've got silicon dioxide, so that's just glass, and then hydrofluoric acid. So hydrofluoric acid is an interesting acid because it actually dissolves glass. So that's not something that the other acids have the ability to do. It turns it into a soluble acid of its own, and then the glass itself dissolves. This is also a way that you can etch glass. So
Oh.
you've probably been to like an office that has the person's name or phone number or business name etched on a piece of glass, and this is how they do it. So somebody will like coat the window in wax, and then they'll use like a X-Acto knife or something and scrape away the part where they want to be etched, and then they'll just pour or put a paste of hydrochloric acid on it and wait. And then
I just thought they used knives.
yeah, it's not. They don't use a grinder or anything like that. It's a chemical etching.
That's pretty cool.
When the last year that I was living in Pennsylvania, this kid got caught. There was like this little vandalism spree where somebody was taking a sponge that had hydrofluoric acid on it and rubbing it right over the section of police car windows where the policeman would be looking out going forward. So it just looks like there's, I don't know, maybe bird poop or a smudge or something on there, and then you go to wash it off and the window's etched. So those windshields at this time, way back in like '98, those things were like $3,000 or $4,000 a piece. And he hit like a dozen police cars in the
Oh no.
Allentown / Bethlehem area before he got caught.
He got caught? That must have been so much money.
It was a lot of money.
And did he get any jail time?
I don't remember if he got jail time. I'm assuming he got some. I don't know, actually.
Because you don't really mess with the police, like, in any way. Or else they'll get mad.
Okay, so the second reaction here is marble. That calcium carbonate. I mean, that's just chalk. when it's in a particular format, it's called marble. And then you have sulfuric acid, and sulfuric acid will dissolve the marble into calcium sulfate, which is soluble, and CO2. And so things that are made out of marble will dissolve when they're exposed to sulfuric acid, in this case, like rain.
Are you talking about like kitchen counter marble?
Okay, but how often is it raining in your kitchen? I mean, I don't know
Yeah,
what your
that's-
house looks like,
that's fair.
but
I just don't have a roof.
I saw one just there.
This this room has a roof, but it's the only
Oh, but
one.
the house doesn't have a roof. Okay, that makes
Yeah,
sense.
no roof.
All right, that's good. All right, I'm pulling something up. Just a second.
Where does it rain? Like acidic rain?
Any place where there's pollution. So we see this picture.
China.
Dang. That's creepy looking.
Oh, that's fun.
How about this picture that you can't really see? Is that better?
Oh no!
Zombies?
I can zoom into it.
I believe this is Washington, and the first picture.
Yeah, I was.
The first picture was taken in
Washington.
1944, and the second picture was taken about 10 years ago
Oh no! Where is that in the?
in the
middle?
Boston area. So
Oh.
what's happened?
Oh.
There's
Oh,
enough
no.
acid rain in the atmosphere that causes the statue itself to dissolve. So really, what's going on is it's dissolving away and turning into a gas and calcium sulfate, which is soluble. There's a huge problem with that in Greece, especially in Athens, because Athens is on it's at the edge of a bay and it's got a backdrop of mountains. So any
Oh.
pollution that builds up inside the city of Athens stays in the city of Athens. So what's Athens
it's like-
famous for?
Athens is made out of like marble and stone.
Made out of marble and stone. Well, it's got a bunch of monuments, right?
Yeah.
And those monuments are made out of marble. Open a new tab. So stuff like the Pantheon and the Acropolis, which is what's here. This might look like it just is falling apart because of wear and tear and whatnot, but actually most of this damage is acid rain damage.
I always thought it was from like
Right.
all the wars that happened in ancient Greece.
Negative. Nope.
Really? That's crazy.
Okay.
Gage, are you still talking about roofs? Ethan, stop lying. You know I don't have a roof.
Cake is a lie. Oh, it's horrible. Okay, so titration. So I would like to be able to titrate stuff, have you guys titrate stuff, but we can't. The titration equipment is kind of spendy, and it's just not something we can do at your house. So you don't get to do the titration. So the way a titration works is you create a solution of known concentration. So usually, because there are so many more acids in the world, usually it's a base being your standard, and the acid is the thing that you're trying to figure out what the concentration is. So those things on the wall next to where I sat in lab, those things are called burettes, and they're very accurate volume measurements. They're 50 milliliters total fluid, and you can measure them down to 2 decimal places of volume release. And so you'd fill those up with a base, you'd put them on a ring stand, and you'd put an acid in an Erlenmeyer flask with a spin magnet and stick it on a magnetic stir plate, and then let the base come out. And the base goes out, and the reason that the acid of unknown concentration down there is pink is because you use a chemical called phenolphthalein. And when phenolphthalein is exposed to hydroxides, so it's in a basic environment, it turns pink. So the color that you would be looking for is something like bad wine, like a blush, or like a white Zinfandel that's not actually white. And you're
A
looking
what?
for a very, very pale pink color. And if you've gone into the like Pinot
Like
Noir, then you've gone too far.
So yeah, white Zinfandel's kind of like that.
Kool-Aid of
Like-
wine.
What about rosé?
Kool-Aid of wine.
Rosé is good.
Some people think Kool-Aid is good.
I like all wines.
Red wine is just so much.
If you gotta have it with the right kind of meal, it's great.
Okay, so the reason that this works is basically it's sort of an on-the-fly Henderson-Hasselbalch equation. So let's look at this graph for a sec. So let's say I take a pH, a probe that can measure pH, and so I've got this acid and it's sitting in this container, and I put my pH probe in. So the pH is going to read very low because it's an acid. And so I'm dripping this base in, and the pH is slowly going up. And then all of a sudden it skyrockets and then levels off again. That point where it starts to skyrocket, that's called, right in the middle is called the equivalence point. And that's when the acid and the base are, their concentrations are equal to each other. There's some mathematical connotations with this. Does anybody know what that means, that point where the equivalence point is mathematically? That somebody might talk about in, I don't know, a calculus class?
Oh, the type of graph it is?
An inflection point.
That is correct. Both of you are correct. That's an inflection point where the concavity of the curve changes. So before pH 7, the curve is concave up. And after pH 7, the curve is concave down. So on our way to 7, the slope keeps going up and up and up. And then as soon as I hit 7, then the slope starts to go down and down and down. But what's the slope at 7 in this particular curve, which is where the inflection point is?
Zero or
It's not.
1.
0 would be flat.
Yeah.
It's undefined.
It's undefined. Exactly.
Damn it.
Undefined because you're dividing by 0. So this is rise over run, and the run is 0 because it's vertical. So that's what your inflection point is. What happens if I take the derivative of this curve?
It turns into a parabola.
Turns into a parabola?
Or am I just crazy? I'm probably just crazy.
I forgot what
I
I'm
should
doing.
not
I
choose
need a
that
math
color.
class.
Ah.
It's weird, like
Sorry, let me choose a
Is it
different,
the U?
let me choose a different color. How about this blue?
Yeah.
Is that enough? Let me make this bigger too.
exponential. No, what is it? Is it 3? Griffin calculator, help me.
Right?
It's going to do that.
Oh.
Because the first derivative is telling you the slope of the curve. So initially the slope isn't very much, starts to go big, then it goes through the roof, and then it comes back down, and it starts to, taper off again, and it's more flat. So that's what your first derivative is going to look like. So you could measure the pH during the course of a titration with a probe, and then find the equivalence point very easily by taking the derivative of all of the data, and whichever point is the highest, that's going to be your equivalence point, because that's going to be the undefined section. All right, so sorry, let's go back up here for a sec. Why does it keep doing that? This is the equivalence point, this is the titration curve for a strong acid being titrated by a strong base. And I know that because the equivalent point is exactly 7. So when the equivalence point is 7, that means I had strong of both of those, because when I'm done with it, you end up having, when they're completely neutralized, all I have is a salt and water, and the salts of a strong acid and a strong base can't change the pH. So this is the equivalence point for a buffered solution. So a buffer is going to have a weak acid in it. And so then when you hit the equivalence point for a weak acid, that means you're going to have a whole bunch of excess base in there because you're creating a salt that has a basic impact on the solution. So your equivalence point is going to be significantly above 7, which is what's shown here. What's going on with this titration curve? Why does it have 2 equivalence points?
Because you added more
No,
base.
no. What happens at the equivalence points? The amount of acid and the amount of base are equal to each other. But what if the acid that I'm using has 2 H's on it? What if it's polyprotic?
Oh,
What if it's H2SO4, which is what this one is? And that's just way too big. So this first H comes off at this equivalence point, and then the second H comes off at the second equivalence point. So if I just keep adding base to this, I'm going to end up with a sulfate polyatomic ion. This first inflection point leaves me with some water and hydrogen sulfate with a minus charge. And then if I keep doing it, my hydrogens, I get more water and then just sulfate. If I was talking about phosphoric acid, you'd have 3 equivalence points because it has 3 protic H's. And the same thing with citric acid that we showed a couple of homeworks ago.
what if we had more than just one acid and one base?
The curve would look a little crazy. And so I tried to do that lab maybe 10 years ago where we titrated Coke. And,
Okay.
and it was hard because Coke has at least four acids in it. So you kept getting all of these mini equivalence points because the equivalence points would be very close to each other. So your curve, or the curve that we generated was like,
Bumpy.
it was very bumpy. It didn't look like a regular titration curve. And the equipment that we were using wasn't very accurate, so I couldn't get exact values for each of these equivalence points. It was hard to get their numbers. But it was interesting because I could do, if we had better equipment, we could hit equivalence points exactly. They have machinery that does titrations for you, and so it's letting in micro drops. And it makes very small changes very easy to do. When you're doing this, the titration, I don't know how many of you have actually done the titration before, maybe in high school or whatnot, but you can be to the point where I think we're just about done. There's like this faint color, like I don't know if it's pink or not, but it could be pink. And then you put one drop in and all of a sudden it's very dark pink, a reddish color. So the reason is this is where phenolphthalein starts to show. So the equivalence point here is 7, and so it doesn't even start to turn pink until 8. But what's the run on this curve? Let me try to make this smaller.
Really long, it looks like, compared to the other.
Okay, so no, that's the exact opposite.
Okay.
Why can't I make this smaller? Negative. I don't know why it keeps jumping back.
So does it start out as clear?
Yeah. Well, it starts out as clear and colorless. Where'd that curve go? Okay, so what's my run in this rise over run equation? Or yeah, sure. Sorry, say again.
30.
Molar MaOH.
It's the concentration of, in this case, 0.5 molar. I don't know, whatever that is. It doesn't really matter. Molar equivalent. So it could be sodium or potassium. Doesn't matter. It just has to be a strong base. So tell me the distance of the run between pH 4 and pH 10. There's pH 4.
So it's
And there's pH 10. What's the distance in the run?
So it's 6/3, so it's 2.
No, the run,
Oh, sorry.
not the rise. The rise would be 6, right? But what's the run
It'd be
difference?
nothing.
It looks almost minuscule, right? It looks like I'm on 20 milliliters, and I definitely added something, but it basically still on 20 milliliters. So a drop can take you from pH 4 to pH 10. So you could mess it up very easily by just adding a single drop. These are different solutions that will change color based on pH. So if the solution that you're looking at, if you're interested in checking the pH between 10 and 11, you can choose this alizarin yellow, R. If you want to check something close to 7, then you can use phenolphthalein, or right on 7, you can use bromothymol blue, and it goes from being yellow to being blue. So there are different indicators that will give you different pH changes over a different range.
So it goes from purple to blue to.
No, these are 5 different indicators.
Oh, okay.
So if we were doing this lab in the lab, we would be using phenolphthalein, and it would go from being completely clear and colorless to being pink. If we were
Okay.
using any of the other ones, they all start yellow, a faint yellow, and then they become more blue or purple depending on which one of these you're using.
Didn't we do a lab like that? Like, wasn't that our last lab?
No.
Last term? Because I remember one of our liquids, it went from like very clear and colorless to just.
That was the clock
very,
reaction lab.
Yeah.
Yeah, that doesn't have anything to do with this. That was iodine reacting with a carbohydrate.
Okay. Oh.
All right. What's this? What's the deal with this titration curve?
It's the opposite of the other ones.
So in my container, in my Erlenmeyer flask, I've got a base, and coming out of the burette is dropping an acid.
Oh.
What's wrong with this titration curve?
It's very smooth. There's no, yeah. There's not a point where it's.
There is an inflection point, but the inflection point itself is what Annika said, is the whole thing's been smoothed out, right? So you've heard a lot of this over the last several weeks. We're practicing social distancing for what reason? What are we trying to do?
To flatten the curve.
Flatten the
Flatten the
curve.
curve, so we don't go over the carrying capacity of our medical staff and stuff.
Exactly. So what's the situation with flattening this curve that we're looking at now? We don't want to overburden our buffer in our bloodstream, so we end up changing our pH of our blood. So what you do is you have a buffered region that you add an acid or a base to it, and the pH barely changes. Instead of this curve here, where all of a sudden there's a vertical point to it. We don't want a vertical point. With your blood pH and the blood buffer, can you imagine that there's a time when it could become vertical?
You're exposed to a massive dose of something that overburdens the buffer.
Yep. So you actually end up
Overdose.
swamping the buffer to the point where it's no longer functioning. Does that make sense?
Yeah.
When I think about it, I think about some World War Z. Did you see that movie?
Unfortunately.
Kind of. I just remember the scene where there's like a big wall and then there's a bunch of zombies.
That's what I'm talking
Right.
about. That people
Yeah.
might remember that because that was part of the trailer. So there's this
Yeah.
giant wall that Jerusalem is behind, and there's zombies over here, and there are people over here. And for some reason, the people started singing, and the singing freaked the zombies out. And so then a zombie ran his face into this wall and died. And then another zombie jumped on top of him and died. And another zombie jumped on top of him. And there were literally hundreds, if not thousands, of zombies dying on top of each other until they got to the top, and then there was a ramp and it came over. So
It's
your
always
bloodstream
higher.
is constantly trying to stop acids and bases from changing it, but at some point you're going to max out the capacity of the buffer. So it's called buffering capacity. Like it could be cold
Buffer
outside, like
incapacity?
20 degrees Fahrenheit outside, and you're wearing a jacket and you're not freezing to death. But then if it's negative 20 degrees outside, maybe that jacket's capacity to keep you warm has been exceeded. And
So we just need to get a Brad Pitt to help us.
What?
yeah, I'm sure he's got a good background in epidemiology and biochemistry.
Oh yeah, haven't you seen the movie? He's super talented with all kinds of stuff.
Yeah.
Somehow.
Oh, the bear movie?
Bear? No.
World War Z.
No,
What
wait,
was
that
it?
was
Oh, that was
Something about the
Oh, then the
wild.
The
Revenant?
Revenant. The Revenant. I got
No,
it first.
no. That's not Brad Pitt.
I know, that's not what you're talking about, but
Well, that's also not Brad Pitt. That's
who was that?
DiCaprio.
it's Leonardo DiCaprio.
Yeah.
That scene was terrifying.
It
I haven't seen
is.
it yet.
It looks terrifying. It is terrifying. I've seen it.
The CGI on it was amazing, and if you haven't seen that movie, and the movie is, I don't know, gross.
Yeah.
Yeah.
There's a
And
lot
he
of
sleeps in a dead
grossness.
horse carcass.
Yeah.
Is it,
So, but if you
like-
want to see what I imagine would happen if a person interacted with a pissed off bear, watch that scene because
It's a mama bear too.
it's phenomenally well done.
Isn't that what he got the Oscar for? The Revenant?
I think.
Yeah,
Yeah.
but I don't know what to tell you. What movies do you watch,
Oh, well,
Kalina?
Y'all were just talking about cold stuff, and so I just immediately thought about The Revenant.
You need to see more good movies.
I
Or
don't.
watch more bad ones like Tusk.
Yeah, I don't know how
Oh
many.
yes. Or The Room.
I really want to watch Inglourious Bastards.
At first, I thought that movie was supposed to be about something that actually happened.
Inglourious Bastards?
Yeah, and then when you get to the end, you're like, "Oh, this is so totally
Yeah,
made up."
that did not
That
happen.
did not happen.
I'm sure like someone has a story similar to that all the way up to the literal end scene.
Sure.
What
Like
about
not having that end scene.
there's one about a pastor that's a raptor and he kills ninjas from China. The Velocipaster.
That can't actually be a thing.
Aren't there like
It's real.
aren't there like 6 or 7 Sharknado movies?
Something like that. There's also a Paramaconda movie.
I'm gonna start muting people because I'm turning into Ethan evidently. Okay, so to calculate concentrations and changes for acids and bases, I gave a pretty complex, like this is every step you need to know, and you could do all of these pieces. After I've added 9.8 milliliters, what would the pH be? The important thing is the concentration of the acid times the volume of the acid is equal to the concentration of the base times the volume of the base at the end point. The end point and the equivalence point are the same thing. So what we're saying is moles acid equal moles base when you're done with the reaction. And this is how we calculate the concentration of the weak acid that we didn't know, or the acid that we didn't know is concentration, because we know exactly how many moles of base. So when we're doing these problems, we know this concentration, the concentration of the base, because we made the base. We know the volume of the base because we were the one using the burette and dribbling the base into the container. We know the concentrate or the volume. Sorry, we don't know that part. We know the volume of the acid because we grabbed the Erlenmeyer flask and we put the acid solution in here. The only thing we don't know is the concentration of the acid, which if I know that variable, and that variable, I can calculate the concentration of the acid. So
And this is just a titration problem.
this is for any titration problem, yeah. must have done 5,000 of them because it was part of my job when I was on the aircraft carrier to titrate for sodium concentrations in steam water.
It reminds me kind of like the PV is equal to nRT, how like you have almost every variable, you just need one, and you just kind of algebra it.
Yep, that's what happens with most of these algebra things. So that's all I got. That's all the notes for acid and bases. We're done with that.
Are we gonna next time or like